So in the previous section, we looked at the Euclidean algorithm for the case of the integers. And this will turn out to be one of the most important tools we use for proving properties of the integers, such as the unique factorization theorem. So I want to pause right here on the set of integers and talk about other types of domains that have such a Euclidean algorithm, because then they'll enjoy a lot of the same properties that the integers have. And these domains are called Euclidean domains. So to recap what we did last time, we have a division algorithm for the integers that said for any a and b, a equals qb plus r for some remainder r strictly less than the divisor b. And as we saw, this was the key property for establishing the Euclidean algorithm. So it's of interest to explore whether there are other integral domains having such a division algorithm. And we'll look at a couple examples today. So if it's been a while since you've had ring theory, you might take a look in the appendix on reviews of groups and rings and browse through those pages a little bit at this point. So just to recall, an integral domain is a commutative ring with unity element 1, so multiplicative identity, having no zero divisors. So what does that mean? That means if you give me any two elements of the ring such that the product is 0, then either A equals 0 or B equals 0. So a zero divisor means some non-zero element of your ring that you can multiply by another non-zero element to get 0. And so an integral domain has no zero divisors. Okay, what's a Euclidean domain? So I'll let D be an integral domain and D star be the set of non-zero elements of D. Then we'll call D a Euclidean domain if there exists a mapping from the non-zero elements into the non-negative integers. So that's what the natural numbers together with 0, that's the non-negative integers, such that two properties hold. First of all, delta of A is less than or equal to delta of A times B for all non-zero elements A, B in the domain, and that should be a D star. Well, they're non-zero elements, so that would be redundant. And property 2, this is the important one, is that we have a division algorithm. So for any elements A and B in the domain D with B not equal to 0, there exist elements Q and R in the domain such that A is Q times B plus R. So we have, you're thinking again that this is modeling A divided by B, and Q would be called the quotient, and R the remainder. Okay, and we have a stipulation that the remainder should be smaller than the divisor. Now what does small mean if we're not in the integers? It means that either the remainder is 0 or delta of R is less than delta of B. So why did I have to work with this function delta? It's because the integral domain itself may not be an ordered set. So what would it mean to say one element of D is smaller than another? So what we have to do is map D star into the natural numbers so that we have a sense of what's bigger in the domain D. And there are other slight variations you can find in this definition in the literature, but we're not going to concern ourselves with those things. They all have this key property number 2, that a Euclidean domain is essentially an integral domain that has a division algorithm. So the set of integers is our standard example of Euclidean domain. So it's a Euclidean domain with respect to the mapping delta of n equals the absolute value of n. Okay, so why is this a Euclidean domain? Well, certainly Z is an integral domain. That's a given. It has no zero divisors. It's commutative. Second thing we need is that delta is a mapping into the non-negative integers, and that's certainly true. This is greater than or equal to 0. Well, I should be more precise there. This is an element of n together with 0 for any integer n. And now the key properties, 1 and 2. So property 1, let's go back and look at that and use the same notation. So I'm starting with two non-zero elements, and I want to show that delta of A is less than or equal to delta of A times B. So let's let A, B be integers that are not zero, so elements of Z star. Delta of A less than or equal to delta of A times B is equivalent to the statement that the absolute value of A is less than or equal to the absolute value of A times B. And I claim that, of course, is trivial because these are non-zero numbers here. So, well, let's use the multiplicative property like that. And since B is non-zero, the absolute value of B is at least 1. So this is true since the absolute value of B is greater than or equal to 1. Okay, so property 1 is straightforward. And then property 2, well, what is that? That is, in fact, the ordinary division algorithm for the integers. So given AB in Z star, we have, let's see, did I specify? Yeah, we don't even need that. We can just take any two integers. B is not equal to 0. That's the way I've stated it. By division algorithm for Z, there exists Q and R in the integers such that A is QB plus R with R between 0 and B. Well, if R is between 0 and B, that would imply that the absolute value of R, and okay, so when B is negative, we need the absolute values here. So this would imply that the absolute value of R is strictly less than the absolute value of B. Okay, so Z is a Euclidean domain. Both properties 1 and 2 hold. So in your homework, you'll take a look at the Gaussian integers and show that they are a Euclidean domain. So what are the Gaussian integers? Let's draw the complex number plane here. So we have the horizontal axis being the real axis and the vertical axis being the imaginary axis, so I, 2i, 3i, and so on. And if we draw this grid of integer points, so what do I mean by that? I mean points with integer coordinates, like that. That set of points is what I mean by the Gaussian integers. So all complex numbers of the form a plus b times I, where a and b are any integers. And note, this is a ring. It's closed under addition. It's closed under multiplication. Being a subset of complex numbers, it enjoys all of the usual properties like associativity, distributive law, commutative laws. It contains the identity elements. 1 is an element of this, and 0. They're both Gaussian integers. Okay, so this is a ring. And plainly, it has no zero divisors, being a subset of the complex numbers. And so it's an integral domain. So in your homework, you're going to show that it's a Euclidean domain with respect to the mapping delta of a plus b is the square of the absolute value. So plainly, this is a mapping from the Gaussian integers into the non-negative integers. Yeah, so if a and b are integers, this is going to be a non-negative integer. And so you're going to have to verify that the division algorithm holds for this mapping. Another example are polynomial rings. So recall, for any field f square bracket x denotes the set of polynomials with coefficients in f, and this is a ring. So a polynomial is just what we always mean by a polynomial, a sum of monomials of arbitrary degree. So the degree n can be any natural number, or it could be 0. Maybe there's just a constant term here. The coefficients have to belong to the given field f. And all of the coefficients. So I goes from 0 to n here. Okay, so again, you can read more about that in the appendix. When you multiply two polynomials, you get a polynomial where the coefficients are back in the field of definition. So this is in fact a ring, and it's an integral domain. So let's see if we can recall why it's an integral domain. I'll let this denote the degree of a polynomial, deg of f of x, denote the degree of a polynomial f of x. So since f is a field, we have this property that the degree of a product of two polynomials is the sum of the degrees of the individual polynomials. Okay, and this is an elementary fact. Where does it follow from? You just look at the leading terms of f of x and g of x, and when you multiply those two polynomials, the leading term of the product is just the product of the leading terms of f and g. Right? So if you have an nth degree polynomial like this, where an does not equal 0, and you have an mth degree polynomial where bm is not 0, multiply them, the leading coefficient is just that, and so the degree is the sum of the degrees of the two polynomials we started with. And this is what makes it an integral domain. It tells you that there's no way you could multiply two non-zero polynomials and end up with a 0 polynomial. The degree only gets bigger. You can't shrink it down to a non-zero, to a 0 constant. Okay, so this is an integral domain, and the question is f bracket x a Euclidean domain? And if so, what is the delta function? So delta, remember, is a mapping into the natural numbers. That kind of gives us a measure of the size of the polynomial. Well, here's a fact from algebra that you've all seen. It's the way we do long division of polynomials. So when we're doing long division, let's say we're looking at f of x divided by g of x. What do? We take f of x, put it under a bracket, we put the divisor g of x over here, go through our long division, and up on top we'll have a quotient, and we have a remainder. And the stipulation is you keep doing the process until the remainder has degree smaller than the divisor. Right? So, the division algorithm says the following. Let f be a field, let f of x and g of x be elements of f square bracket x with g not equal to 0. Then there exist polynomials q and r such that f is q of x times g of x plus r of x, where the remainder r of x is either 0 or its degree is strictly smaller than the degree of the divisor. Now I need to put this stipulation here because the degree of 0 is undefined. If you have a non-zero constant, we say the degree is 0. But for the 0 polynomial, we'll say the degree is undefined. Otherwise, we would violate that the rule that says the degree of the product is the sum of the degrees. So again, q is called the quotient, and r is called the remainder. So I have a proof in Appendix D, and you can take a look at that if you like. But this is telling us, we have a division algorithm, and when there's a division algorithm, we get a Euclidean domain. What's the delta mapping? Well, it's just the degree of the polynomial. So when you take the degree of a polynomial, you end up with a natural number, or you get 0 in case it's a constant. So any polynomial ring over a field is a Euclidean domain with respect to the mapping delta of f of x is the degree of f. So again, just check those key properties. So we're starting with an integral domain, f bracket x. And we've already noticed the degree is, in fact, a mapping into the non-negative integers. So we need to have the delta a less than or equal to delta ab property. Well, for our case, what does that mean? Delta of f of x should be less than or equal to delta of f of x g of x for any polynomials f of x and g of x. Well, why is that true? This is the degree of f of x, and that needs to be less than or equal to the degree of f of x times g of x, which is just the sum of the degrees. And that is certainly true, because this is at least 0 right here. The second property is just the division algorithm theorem that we've stated right here. So this is the division algorithm. All right, in the definition of a Euclidean domain, you have to have a quotient and remainder where the remainder is either 0 or delta of R is less than delta of G. And that's exactly what we have in this statement. Okay, so that's another standard example of a Euclidean domain. The concept of divisibility and greatest common divisor can be defined just as we did for the integers. The only difference is in the meaning of the word greatest. So here greatest means with respect to the mapping delta. So if I let A and B be two elements of your integral domain, and you want to talk about the greatest common divisor, so it has the usual properties. D has to be a common divisor, and D is the common divisor having the greatest delta value. So delta D is maximal. Okay, and it follows by part 1, by property 1 of the Euclidean domain, not this part 1, but part 1 in the definition of Euclidean domain, that if A is a non-zero element in your domain and D is a divisor of A, then delta of D is less than or equal to delta of A. After all, D divides A means that dx equals A for some x in your integral domain. And that would mean that delta of D is less than or equal to delta of dx. Okay, so that's the property 1 in the definition of Euclidean domain, which equals delta of A. So delta of D is less than or equal to delta of A. Thus, if A is a divisor of B and B is a divisor of A, that is, A and B differ by a unit multiple. Okay, that word differ can be misleading. This just means A equals B times a unit for some unit, U. Then the delta values of A and B are equal. So why is that? Well, if A divides B, that means that delta of A is less than or equal to delta of B, and B divides A means that delta of B is less than or equal to that. And you put these two together, and we get equality. Okay, item 4. The greatest common divisor of two elements of a Euclidean domain is unique up to unit multiples. So one direction of this is straightforward. So if we have AB equals D, I can also say that DU is a greatest common divisor for any unit. Because if D is a common divisor of A and B, then D times U is also a common divisor of A times B, and delta of D times U equals delta of D by item 3 that we just looked at. If two things differ by a unit multiple, then they have the same delta value. So the other part that it's unique up to unit multiples, in other words, that if E was any other greatest common factor of A and B, then it must differ from D by a unit multiple. That will follow from a property we'll study later. Later we'll see that Euclidean domains are PIDs. And that will complete this uniqueness part. So don't worry about that for the time being. And then item number 5. So once we have a Euclidean domain, we can establish a Euclidean algorithm just as we did in the previous section with the integers. So we can find the greatest common divisor of any two non-zero elements of a Euclidean domain by repeated applications of the division algorithm. So you would have A is Q1B plus R1, and then you're saying, okay, I'm going to subtract Q1B from A to get R1, and then we take B and we say, well, that's Q2 R1 plus R2, and you subtract Q2 R1s from B. So, I didn't state it, but by the way, the GCD invariance property would work just as well for any Euclidean domain. And so you go through the Euclidean algorithm, and with the integers, we had a decreasing, strictly decreasing set of remainders like this, so we knew it would terminate. With a Euclidean domain, we have a strictly decreasing sequence of delta values, because at each stage, delta of R1 is less than delta of B, delta of R2 is less than delta of R1, and so we get this monotone decrease in sequence of positive integers, so it has to terminate. And just to recap, for polynomial rings, the set of units are just non-zero constant polynomials. So to be a unit means that it has a multiplicative inverse. So units are elements having multiplicative inverses. And the only polynomials that have multiplicative inverses are non-zero constant polynomials. As soon as you have an x, you get a rational function, which is no longer a polynomial if you want to take its multiplicative inverse. And we had observed that greatest common divisors are only unique up to unit multiples. So for polynomials, greatest common divisors are unique up to constant multiples.